The research question for this segment was, what features or characteristics of a molecule contribute to the complexity of energy levels that electrons can be excited to, or the number of energy levels that electrons can be excited to, and how does that impact peak shape? Compared to the peak for absorption, the peak for emission was shifted to the right for both the green dye and the red dye, meaning the substance is emitting light at lower energy levels compared to the light it absorbed when it was excited. This is because after electrons have been excited, they lose some of their vibrational energy to the environment, and so they're in a lower energy state compared to their original excitation energy state. The more vibrational energy they lose in the excited state, the larger the shift between absorption and emission spectrums. Thus, when these lower energy electrons emit light and return back to the ground state, the emitted light would have a longer wavelength than the excitation wavelength, so the energy would be lower. Emission and absorption spectra more or less mirror each other because after electrons are excited, they lose some of their vibrational energy, but then when they return back to the ground state, they return to the highest vibrational energy level of the ground state, causing the shape to be mirrored. Additionally, emission intensities are lower compared to the absorption intensities. This is because some of the dye molecules are decomposed because of the light intensity in the presence of oxygen, or because some of the energy is transferred to other molecules that are physically close to the dye molecules, causing emission intensities to be lower. For emission spectra for both the green and red dyes, it can be seen that the red dye absorbs a larger range of wavelengths of energy than the green dye, but has a lower overall intensity for those wavelengths compared to the green dye, which absorbs a smaller range of wavelengths of energy, but has higher intensity for that range of wavelengths. This means the red dye emits light at a slower rate than the green dye, thus resulting in a lower intensity. This also means that the red glow stick would last longer than the green glow stick since it's emitting light at a slower rate. The peak shape can be attributed to how the red dye molecule has more energy levels than the green dye molecule and thus emits more wavelengths of energy because there are more ways for electrons to return to lower energy levels compared to the green dye molecule. Ultimately, we predict that if the length of time between excitation and relaxation of electrons increases, then the emission peak would have a greater shift to the right and lower intensity, but still have a mirrored shape. Also, we predict that if energy input controls the complexity or the number of energy levels, then when energy input increases, the absorption peak shape would increase in intensity and the emission peak shape would also increase in intensity.
This is analogous to different units of measurement. For example, over 63,000 inches make up 1 mile. However, 5,280 feet make up 1 mile, and 1,760 yards make up 1 mile. So the shorter units of distance, like inches and feet, require a higher number to reach the end goal, 1 mile. The longer units of distance, like yards and miles, require a lower number to reach the end goal, 1 mile. The overall distance is the same, just like the overall energy input is the same. But if the units are smaller, more of them are needed to reach the same distance. But if the units are larger, similar to how the red dye absorbs more wavelengths of energy, fewer units are needed to reach the same distance.